Understanding the need for a t-distribution requires a little bit more understanding of the mathematics behind how we calculate standard error. We're going through this fairly quickly because really understanding the need for a t-distribution is not a necessary part of this course. If you recall our standard deviation formula from Chapter 2 when we were just looking at before we started to look at inference at all, we said the standard deviation of a data set can be calculated using this formula for S. Note that what this really has in it is a sum of squares. So we're going to take every value in our data set, and for each of those values subtract off the mean, square it, and then add them all up. That's what that big sigma means, is sum. We end up taking a square root and scaling it by that n minus 1. So that sum of squares then goes into our standard error calculation. It is the numerator, right? That whole formula for S comes in here and then gets divided by the square root of n, so that if we are looking at a way to standardize this distribution, and by standardize I mean kind of like with the normal distribution when we went from a single observation to its z-score or its z-test statistic later on, we would subtract off the mean and then divide by the standard deviation so that we could look at a single distribution that's assuming a mean of 0 and a standard deviation of 1. So that gets us to this formula for t. Now, the only problem with this is that when we're using an estimate of standard error that is based on the sample, the thing that we get from this formula no longer follows an exactly normal distribution. So this follows what we call a t-distribution. And a t-distribution looks pretty similar to a normal distribution in that it is still bell-shaped and symmetric, right? It's just that it has thicker tails. So it has more of the mass of the distribution in the tails and less concentrated at the center. Another thing about t-distributions is there isn't just one. We have just one standard normal distribution, but we have lots and lots of t-distributions. So we have a few drawn here so that we can see the comparison between them and the normal distribution. For example, for n equals 2, meaning a sample size of 2, we have the distribution that I have just now outlined in pink. And for n equals 10, we have the distribution that I have just highlighted here in blue. Now what we can see is that for a smaller sample, we have less concentration at the center and more mass in the tails, and that as n increases, so we look at 10 versus 2, we're getting closer to a normal distribution. And that's why it is that with the normal distribution, we say in parentheses, it's like n equals infinity. If we had a t-distribution with infinitely many degrees of freedom, it would be the same as the normal distribution. But in practice, what happens is that a t-distribution with a very large number of degrees of freedom is so close to the normal distribution that we just go ahead and use the normal distribution at some point. The number of degrees of freedom is based on the standard error calculation. So again, that brings us back to the standard deviation formula, which then feeds directly into that standard error formula. And it's because it's the number of independent terms in the standard error calculation. We would add up n terms here because there would be one term for each value of x. We say there are only n minus 1 independent terms because if we know the mean and we know n minus 1 of those x values, we could theoretically back calculate the remaining one. Therefore, it is not fully independent. So the part that we really need to know from all of this is that when we're doing inference for a mean, we have a t-distribution with n-1 degrees of freedom, and we want to understand that these t-distributions do resemble the normal distribution, even though they are their own class of distributions, and we have a whole bunch of them, one for each number of degrees of freedom. They do get closer to the normal distribution as the number of degrees of freedom increases. That's also helpful to know. We have conditions for using a t-distribution for inference about a mean, just like we had conditions for using a normal distribution. The general rule is that if our sample size is large enough, we assume it's going to be okay regardless of the shape of the sample, which we assume is the same approximate shape as the population. Now, large enough we can quantify using this rule of thumb, in which we say if n is at least 30, we generally assume that it's reasonable to use a t-distribution for inference. Now, I say generally assume here because there are exceptions. And if we know about the shape of the distribution, then we might know that in fact it's not reasonable to use a t-distribution even in cases where n is at least 30. But if we don't know the shape and we know that n is at least 30, we can generally assume that it's reasonable to use a t-distribution. If n is less than 30, we want the sample to be fairly symmetric and unimodal. The closer that n is to a normal or t-distribution type of shape, the smaller n that we can get away with. So let's look at a few examples here. In our first image, we have n equals 30, and it looks like the shape is not too bad. It's not a perfect bell shape, but it doesn't have extreme skew or extreme outliers. And we have n equals 30, which is our minimum size for assuming that even if the shape isn't that great, we can probably get by. There's no particularly difficult judgment call to make here. We would say that yes, conditions are definitely met. We have both shape and size in this distribution. Looking at the next picture, it's not quite as much of a slam dunk because we do have some pretty noticeable right skew, but we do have n equals 30 and our skew is not really extreme. It's only if we had a really extreme outlier or several very extreme outliers that we might still have problems even with n equals 30. So here we could also say yes, the conditions are met. And it's largely the sample size, the sample being large enough, that was our reason. In this first example, we had both sample size and shape on our side. On this second one, it's more the sample size that's our reason for saying yes. The next one, we see n equals 8, and it looks like we do have some pretty serious left skew. N equals 8 is not only less than 30, it is substantially less than 30. Keep in mind, every time we answer a question about conditions for using a t-distribution, there is a little bit of a judgment call involved. We have summarized it as a very short rule of thumb, but we want to keep in mind that it's not just that if n is less than 30, it has to be absolutely perfect. It's that the further away from 30 we get on the low end, the closer to bell-shaped the data need to be. So this combination, I would be inclined to say no, that conditions are not met. But someone could argue that they are. So sometimes it's more about how we make the argument than it is about whether we answered yes or no. If one were to make the argument that conditions are met on this, they might say, Even though it doesn't look like a really nice bell shape, the points are all pretty clustered close together, and the bigger problems tend to occur with extreme outliers. We don't see extreme outliers here. It probably wouldn't be too far off to use a t-distribution for inference, but I'm going to go with no here because we do have some clear signs of left skew, and that n equals 8 is starting to get pretty small. Looking at the next distribution, we certainly do see some right skew, but it is not extreme right skew. We also see that n equals 20, and 20 is less than 30, but it's not a lot less than 30. So based on this combination that we're not a lot less than 30 and that our skew is not extreme, I would put these two pieces together and say that yes, conditions are met. I'm going to start answering a little bit more shortly here just to save time in writing, but of course we're just doing a little bit of a drill on conditions now. When we actually check conditions in inference, we say a little bit more than what we are saying here. At least more than what we're saying on some of these. I would say the amount that we said on n equals 8 is a good amount to justify that we really have checked conditions. Now going on to this next one, this one's a little bit more of a judgment call at n equals 10. If I draw out this shape, it does not look perfectly bell-shaped. It definitely has a little bit of a maybe bimodal kind of quality going on, but with small values of n, you hardly even can get a perfect bell shape because there's so few points to stack up that if they all seem pretty well clustered together and n is at least 10, that's often good enough. So n equals 10 is getting pretty small, but it's not that small. So we have less than 30, but we don't have any extreme skew or outliers. I wouldn't even call this skew. I would say it's more a bimodal issue. So no skew, or if there's any, maybe it's a slight left skew, and no outliers. Those are the real things that can cause issues. I'm going to go with yes on this one also. But again, this is one of those examples where somebody could also say no here, and if they justified it pretty well by saying n equals 10 is getting pretty small and it doesn't look like a nice little bell curve or normal shaped sample, so I'm going to go with no, I would think that that was also a reasonable answer. The last one, n equals 20. So we saw already that with n equals 20, we really can have a little bit of skew, but if we have an extreme outlier like we have here, then we start to really get concerned. I'm going to go with no on this one. We have an extreme outlier. Even if n were 30, I would have some doubt about that outlier. But we can go ahead and throw both of these things in. We have an extreme outlier and n is less than 30. So anytime we're checking conditions for using a t-distribution, keep in mind that it really is two things we're looking at. It's the sample size and the shape of the distribution, the shape of the original sample. They have to work together in a little bit of a balance. The larger n is, the less you care about the shape of the sample, but the smaller n is, the closer to a nice little bell curve that sample should be.